Okay, in today's lecture, we'll be covering the second half of the section 5.2 material on infinite series. And to start out this second half, we're going to introduce a special series called a geometric series. So let's start by defining it. We would say a geometric series is any series of the form where we're taking the sum from n equals 0 to infinity of a times r to the nth power, where a is a constant and r is another constant called the ratio of that series. So this geometric series, if we expand it and write out the first few terms, we're taking a plus a times r plus a times r squared, a times r cubed, a times r to the fourth, and so on. So for this special type of series known as a geometric series, if we're interested in determining whether it converges or diverges, we would apply the following theorem known as the geometric series test. So what this result says is that the geometric series a times r to the n, taking the sum from n equals 0 to infinity, will converge as long as the absolute value of the ratio is less than 1, and it will diverge if the absolute value of our ratio is greater than or equal to 1. Now, in the event that the absolute value of r is less than 1, then that means our series converges. And in the case of a geometric series, we can find the sum of our series, which would be given by a over 1 minus r. Now, one thing that we have to be a little bit careful of when we consider some examples a bit later in this section, this formula that we have for the sum, a over 1 minus r, is only valid in the case that we express our geometric series in this exact form, where n starts at 0 and then moves outward to infinity. So in some examples we'll have a sum that starts at a value other than n equals 0, in which case we have to rewrite our series so that it has this so-called standard form. So let's look at the proof of this result. When we're trying to determine convergence or divergence of an infinite series, we want to look at the sequence of partial sums. So let us let Sn be the sequence of partial sums. So if we were to write out the nth partial sum, we would have the sum of the first n terms of our series. So we would start with a plus a times r to the first plus a times r squared plus a times r cubed, and so on, until we have a times r to the nth. Now if we take that nth partial sum and multiply by r, we have r times s sub n, which would be a times r plus a times r squared plus a r cubed, and so on, until we get a r to the n plus 1. So if we were to take the difference in these quantities, that is Sn minus r times Sn, let's look at which terms we're left with. Most of our terms are going to cancel. So taking the difference in these two equations, we see that our a times r cancels, a times r squared, a times r cubed, and so on, up through a times r to the n, which will cancel with a times r to the n, the term that appears just before that a times r to the n plus 1 power. So the only terms that we're left with when we take this difference are a minus a times r to the n plus 1 power. So on this left-hand side of our equation, we can factor out the nth partial sum, and we're left with 1 minus r is equal to, on the right-hand side, we can factor out an a, and we're left with 1 minus r to the n plus 1. So solving for the nth partial sum, Sn, we have a times 1 minus r to the n plus 1 all over 1 minus r, or we could rewrite this as a over 1 minus r times 1 minus r to the n plus 1. So to determine whether our infinite series converges or diverges, we would be looking at the limit of this nth partial sum. So here, taking the limit as n approaches infinity of s sub n, well, we see the only term that depends on n is this r to the n plus 1 power. And as long as this base of that exponential, r, is less than 1 in absolute value, when we take that quantity to higher and higher powers, we get a term which is approaching 0. So, as n gets large, the limiting value for our nth partial sum will be a over 1 minus r, provided that the absolute value of that ratio is less than 1. We need that condition on our ratio to ensure that this r to the n plus 1 power approaches 0. If we had some number r that was greater than 1 in absolute value, let's say 2, if we took higher and higher powers of 2, we would have something that diverges to infinity. So we only have convergence then, in this case that r is less than 1, and the sum of our series is this a over 1 minus r. All right. So let's look at some examples determining the convergence or divergence of a geometric series. So in this next example, we are given some series. We're asked to determine whether it converges or diverges, and if it converges, find its sum. So in part A, we have the sum from n equals 0 to infinity of 1/2 times 1/3 to the nth power. So this is exactly the form of a geometric series. We have the sum from 0 to infinity of some constant a times a ratio of r, in this case r is 1/3, to the nth power. To determine convergence or divergence for this series, we would look at the absolute value of the ratio r. So in this case, that is the absolute value of 1/3, which is 1/3, and that is a value less than 1. So we can say the series converges by the geometric series test. So we know that our series converges by applying the geometric series test. The absolute value of our ratio r was less than 1. Now, if it converges, we were asked to find the sum. So let's think about how we would find the sum. The sum is given by the ratio a over 1 minus r. And in this example, a is 1/2. We're dividing by 1 minus r, which was 1/3. So we're left with 1/2 over 2/3. And recall, to divide fractions, we would take our numerator, 1/2, and multiply by the reciprocal of the denominator, 3/2. So this leaves us with a sum of our series of 3/4. So let's look at another one, maybe not so straightforward. In part B, we've got the sum from n equals 1 to infinity of 5 times 2/7 to the nth power. So this looks very similar to that standard form for a geometric series. The only difference here is that the first term in our summation corresponds to n equals 1 instead of n equals 0. So in order to use the formula for the sum of a geometric series that we had in our theorem, we mentioned that we need this first term to correspond to n equals 0. So let's think about how we could force this first term to start at n equals 0. So if I change the initial value of n from 1 to 0, that is if I subtract 1 from the value of n, then everywhere I had the expression n within my series, I need to increase it by 1. I need to make it an n plus 1, so that now if n is 0, I have the same value that I would if n equals 1 for that first term. So now this looks a little closer to the standard form for a geometric series, but instead of having our ratio r to the nth power, it's now being raised to the n plus 1 power. But if we rewrite this, we could express it in that standard form. So here, this 2/7 to the n plus 1 can be rewritten as 2/7 to the first power times 2/7 to the nth power. And if I combine these first two constant terms, I would have the sum from n equals 0 to infinity of 10/7 times 2/7 to the nth power, and this now has the standard form for a geometric series. This has the form where we're summing from 0 to infinity, some constant a times a constant r to the nth power. Now, to determine the convergence or divergence of this series, we look at the absolute value of the ratio r, in this case the absolute value of 2/7, which is 2/7, and that is less than 1. So we know by the geometric series test, this series converges. So let's say the series converges by the geometric series test. Now, since it converges, we need to find the sum of this series. And the sum is given by the ratio a over 1 minus r. So in this example, a was 10/7, and then we're dividing by 1 minus r, which is 2/7. So we're left with 10/7 over 1 minus 2/7 would be 5/7. So we have 10/7 times the reciprocal of our denominator, which would be 7/5. So this leaves us with 10/5, or 2, for the sum of this series. So in this second example, we saw that we may have to manipulate our series in order to make it start at n equals 0, in order to apply the formula for the sum of our series. So let's look at another one. In part C, we have the sum from 0 to infinity of 2 to the 3n over 5 to the n plus 1. So this looks sort of similar to a geometric series, but it's not written in that standard form. But again, if we manipulate the expression for this general term, for the nth term of our series, we can put it in that standard form. So here we have the sum from n equals 0 to infinity, And our numerator, 2 to the 3n power, can be rewritten as 2 cubed and then taken to the nth power. And our denominator, 5 to the n plus 1, can be rewritten as 5 to the first times 5 to the nth. Now, this can be simplified as the sum from 0 to infinity. And our numerator is 2 cubed, or 8 to the nth power. And then we're dividing by 5 times 5 to the nth. So if we group the two terms that are being raised to the nth power together as a single ratio, we're left with the sum from n equals 0 to infinity of 8 over 5 to the nth power with a constant of 1/5 out in front. So this now has the standard form for a geometric series where our constant a is 1/5 and the ratio r is 8/5. So to determine convergence or divergence of this series, we look at the absolute value of the ratio, which in this case is 8/5, and 8/5 is a ratio which is greater than 1. Now recall the geometric series test says if this absolute value of our ratio is greater than 1, the series diverges. So here we say the series diverges by the geometric series test. So as we keep adding terms in our infinite series, we get something which is diverging. There is no number which the sum of this series is approaching. So let's look at another one. In part D, we have the sum from n equals 1 to infinity of -1 to the nth plus 3 to the n minus 1 all over 4 to the nth. So we might start here by splitting the sum in this fraction. Here we have a sum of terms where the expression for our nth term is the sum of two fractions. So we could first think about splitting that sum as -1 to the nth over 4 to the nth plus 3 to the n minus 1 over 4 to the nth. So now we see that each of these individual terms looks more similar to the standard form for a geometric series. However, this sum is starting at a value of n equals 1 instead of n equals 0. So if we want to rewrite this as a summation starting at n equals 0, we could force it to start at n equals 0 by changing all of the n terms in our summation to n plus 1s. So that would leave us with the following. Now, if I'm taking a sum of the sum of two terms, well, we can think about taking the summation of each of these terms respectively. And if these two series converge, then the summation would be the sum of the sums of each of these series. So in this first series, we can rewrite our general term a little bit. So here in our numerator, the -1 to the n plus 1 can be rewritten as -1 to the first times -1 to the nth over, doing the same for our denominator, 4 to the n plus 1 is the same as 4 to the first times 4 to the nth. And we are then adding the sum from 0 to infinity of 3 to the nth over 4 times 4 to the nth. So rewriting my series once more, we would have the sum from 0 to infinity of a -1/4 times -1/4 to the nth power, plus the sum from n equals 0 to infinity of 1/4 times 3/4 to the nth power. So each of these series has the standard form for a geometric series. This first one, we've got the sum from 0 to infinity of a constant, let's call it a1, times a ratio r1 to the nth power, plus the sum from 0 to infinity of a constant a2 times a ratio r2 to the nth power. So to determine convergence or divergence of each part, we need to examine the absolute value of these ratios. So here, the absolute value of R1 is the absolute value of -1/4, which would give us a +1/4, which is less than 1. And the absolute value of R2, which was 3/4, is 3/4, which is again less than 1. So both of these geometric series converge, which means that the sum of those two series also converges. So we can say that the series converges by the geometric series test. And since this series converges, we have to find its sum. So here, the sum would be the sum of the two series. Now to find the sum of this first term, we would be looking at a1 over 1 minus r1. And then we are adding the sum of our second series, which would be given by a2 over 1 minus r2. So let's see what we get. For our first series, a1 was -1/4. Then we've got division by 1 minus r1. Now r1 was -1/4, so we've got 1 plus 1/4. And then we're adding a2, which was 1/4, over 1 minus r2, which was 3/4. So simplifying, we have a -1/4 over 5/4 plus 1/4 over 1/4. So this leaves us with -1/5 plus 1, or 4/5 for the sum of this series. So here we see that if we have an infinite series where our general term is the sum of terms, we could think about splitting the summation into two pieces and then determine the convergence or divergence of each piece. And as long as both series converge, then the sum would be found by taking the sum of the sums of those individual series. So let's look at another one. In our next example, we have the series 7 plus 2 plus 4/7 plus 8 over 49, and so on. So here, the first four terms of our series are given, but it's not written using the sigma notation. So we first need to establish what is the general form of the nth term in this summation so that we can write it in sigma or series notation. For this example, let's think about factoring out this lead constant of 7. We know that for a geometric series, the first term is usually what we're calling the constant a. So if we were to factor out a constant a, or 7, from each of these terms, we're left with 1 plus 2 over 7 plus 4, which would be 2 squared, over 7 squared, plus 8, which is 2 cubed, over 7 cubed, and so on. So here we would have 7 times 1 plus 2 sevenths plus 2 over 7 squared plus 2 over 7 cubed, and so on. So this allows us to recognize the general pattern for the nth term of our series, and we could write this as the sum from 0 to infinity of 7 times 2 over 7 to the nth power, where we start at n equals 0, so that when n equals 0, that first term would be 7 times 1. So we recognize this as having the standard form of a geometric series, and to determine whether this converges or diverges, we would be looking at the absolute value of the ratio r. In this case, 2 sevenths, which is less than 1. So since the absolute value of our ratio is less than 1, we know the series converges by the geometric series test. Now, since this series converges, we need to find its sum. And here, the sum would be given by a over 1 minus r. In this case, a is 7, and then we're dividing by 1 minus the ratio, which is 2 sevenths. So we're left with 7 over 5 sevenths, which would give us 7 times 7 over 5, or 49 over 5 for the sum of this series. So let's look at one last example for a geometric series. In part F, we have the sum from n equals 2 to infinity of 5 over 2 raised to the 2n power. So here, the first thing that I might do is rewrite my denominator. Instead of 2 to the 2n power, we can think of this as 2 squared quantity raised to the nth. So this is the sum from 2 to infinity of 5 over 4 to the nth power. Now, this is almost the standard form for a geometric series. However, the first term in our summation corresponds to n equals 2 instead of n equals 0. Now, if we force the first term of our series to correspond to n equals 0, that is, if I subtract 2 from the starting value of n, then everywhere within my series I need to add 2. So my denominator, 4 to the nth, becomes 4 to the n plus 2 if I want the first term to correspond to n equals 0. Now, this can be rewritten as the sum from 0 to infinity of 5 divided by 4 squared times 4 to the nth. Or if I group my constant terms, I would have a ratio of 5 over 4 squared over 16 times 1 over 4 to the nth power. And this now has the standard form for a geometric series where my constant a is 5/16 and the ratio r is 1/4. So to determine convergence or divergence, we look at the absolute value of our ratio, which is 1/4, which is less than 1. So we know that the series converges by the geometric series test. And since this series converges, we need to find its sum. And the sum is given by a over 1 minus r, where a was 5/16, and we're dividing by 1 minus 1/4. So we have 5 over 16 divided by 3/4, which would be 5 over 16 times the reciprocal of our denominator, 4/3. So here we can cancel 1 factor of 4 on top and bottom, and we're left with 5 over 12 for the sum of this series. Now in our next example, we are considering a series that might depend on some variable x. So here we're looking at the series where we're taking the sum from n equals 1 to infinity of x minus 5 to the nth, and we're asked to find the values of x for which this series will converge. And for those values of x, we want to find the sum of that series. So in this example, we have a sum starting at n equals 1 to infinity of x minus 5 to the nth. So this is sort of similar to a geometric series where the ratio r is now dependent on x. It's given by x minus 5. Now we know in order for this series to converge, we would need the absolute value of our ratio, that is the absolute value of r, to be less than 1. So we can say that our series converges if the absolute value of x minus 5 is less than 1, which means that the quantity inside the absolute value, x minus 5, is less than positive 1, but greater than negative 1. So to solve for x, we could add 5 through our inequality, and we have 4 is less than x, which is less than 6. So we found the values of x for which our series will converge, and then we're asked to find the sum of the series for those values. Now, in order to find the sum of our series, we need to rewrite this series so that its initial term corresponds to n equals 0. So let's take our summation from 1 to infinity of x minus 5 to the nth and rewrite it as a summation starting at n equals 0. So to do this, we would have to replace all of our n's with n plus 1s in the formula for our series. And we can then rewrite this as the sum from 0 to infinity of x minus 5 to the first times x minus 5 to the nth. And this looks like the form of a geometric series where our first term is a, and then we have our constant r to the nth power. So we had already said that this series will converge as long as the value of x is between 4 and 6. So if we have x in that range, then the sum of our series would be given by a over 1 minus r, or in this example, a is x minus 5 over 1 minus r, which was x minus 5. So that leaves us with x minus 5 over 6 minus x for the sum of our series. Now, in the last part of this section, we will talk about another test for convergence or divergence of a series, which is known as the test for divergence. And usually, when we're testing series for convergence or divergence, this is one of the first tests that we would want to try because it's so easy to apply. So throughout Chapter 5, we're going to learn several different tests for convergence or divergence. And usually one aspect of this material that students struggle with is they ask, well, which test should I be using? And a good recommendation is for any series, the very first test that you would want to try is this test for divergence. And here's what this theorem says. If we're looking at a series summing from n equals 1 to infinity of a sub n, if the limiting value of this a sub n term as n approaches infinity is anything other than 0, then the series diverges. Now, a word of warning about this result, something that students typically try to do is apply the converse of this theorem, which is not true. So as a word of warning, the converse of this theorem is not necessarily true. So what I mean by that is just because the limiting value of this an term is 0, that does not necessarily mean that the series a sub n converges. So let's look at some examples applying this test for divergence. So here we are asked, what can we conclude about the following series, if anything, applying this test for divergence? So in our first example, part A, we have the sum from 0 to infinity of this ratio of terms, 2n plus 3 over 5n minus 7. So here, the general term, a sub n, is given by 2n plus 3 over 5n minus 7. And if we look at the limit of this term, an, as n becomes large, well, we're looking at the infinite limit of a rational function where we have the same highest power of n on top and bottom. So that means that the limiting value would be given by the ratio of those lead coefficients for the highest powers, in this case 2/5, which is a number other than 0. So in the event that we have a non-zero limit, we would say the series diverges by the test for divergence. So here in part A, we could tell that our series will diverge. Now in part B, we have a different series, the sum from 1 to infinity of arctangent of n. So again, if we look at the limiting value of this general term, arctangent of n, as n approaches infinity, we get a limiting value of pi over 2, which is non-zero. So since we have a non-zero value for our limit, that means that the series diverges by the test for divergence. Now in the next part, part C, we have the sum from 1 to infinity of n over the natural log of n. So again, taking the limit of this general term as n becomes large, well, we have something of the form infinity over infinity, which is an indeterminate form for a limit. But if we apply Hopital's rule, we would have the limit as n approaches infinity of 1 divided by the derivative of log n is 1 over n. So this would be the limit as n approaches infinity of n, which does not exist. The values diverge towards infinity. So if we have any limit other than 0, that means that the series diverges by this test for divergence. And in our last example, part D, we have the sum from 1 to infinity of n over n squared plus 1. So if we take the limit of this general term as n gets large, we have the infinite limit of a rational function where the highest power of n is in the denominator. We have n squared in the denominator and n to the first in the numerator, which means that as n gets larger, our denominator increases more rapidly than the numerator. So we would have a 0 limit for the limiting value of this function, or alternatively, we could apply Hopital's rule, and we would have the limit as n approaches infinity of the derivative of our numerator, which is 1, divided by the derivative of our denominator, 2n, and as n becomes large, 1 over 2n tends to 0. So either approach we want to use there, we get a 0 value for our limit. So the question is, does that mean that this series converges? Well, not necessarily. Recall here that the converse of the test for divergence is not true. Just because the limiting value of the term of our series is 0, we cannot conclude anything about the convergence of our series. So in this last part, we have no conclusion for convergence or divergence.